This video is an overview of some of the content learned in Organic Chemistry 1. These are the main compounds covered that I will be talking about today. What are alkanes and cycloalkanes? Alkanes are saturated hydrocarbons in which all of the bonds are single bonds. They are subdivided into the following three groups: linear straight-chain alkanes, branched alkanes, and cycloalkanes. Alkanes are the simplest and least reactive hydrocarbon species containing only carbons and hydrocarbons. Cycloalkanes are alkanes that contain a ring of 3 or more carbons. The chemical and physical properties of alkanes and cycloalkanes. They are nonpolar and insoluble in water. The forces of attraction between alkane molecules are induced dipole attractive forces. The boiling points of alkanes increase as the number of carbon atoms increases. Branched alkanes have lower boiling points than their unbranched isomers. The isomer, of course, has the same number of atoms and electrons, but a molecule of a branched alkane has a smaller surface area than an unbranched one. Although alkanes are the least reactive hydrocarbon species, alkanes and cycloalkanes burn in the air to give carbon dioxide, water, and heat. This process is called as combustion, and that reaction is shown right here. The importance of grasping the nomenclature of organic compounds is a crucial first step to understanding them and their properties, reactions, and so on. So starting with the nomenclature of alkanes, you identify the longest continuous carbon chain and count the number of carbon atoms there are. For example, the reaction shown here, there are 5 carbons. So you look at the IUPAC names table to find the parent name that correlates to the number of carbon atoms. In this case, the parent name of the molecule is pentane. Next, you identify the substituent groups attached to the parent. Again, referencing this example shown here, there are 2 methyl groups. Next, number the longest continuous carbon chain in the direction that gives the lowest number to the substituent at the first point of branching. And then finally, name the compound. The parent alkane will be the last part of the name and is preceded by the names of their substituents and their numerical locations. Hyphens are used to separate the numerical locations from the words. The name is 2-methylpentane. Nomenclature of cycloalkanes. Cycloalkanes are named by adding the prefix cyclo to the name of the unbranched alkane with the same number of carbons as the ring. In the example on the left, there are 5 carbons in the ring, which correlates to the parent name pentane. So it reads cyclopentane. Identifying their substituents goes the same way as it did for the alkanes, and their positions are specified by numbering the carbon atoms of the ring and the direction that gives the lowest number to the substituents at the point of difference. The substituent name goes in front, reading methylcyclopentane, since methyl is the substituent. When the ring contains fewer carbon atoms than an alkyl group attached to it, the compound is named as an alkane, and the ring is treated as a cycloalkyl substituent. An example of this is shown on the right with the molecule 1-cyclopropylbutane. Moving on to nomenclature of alcohols. Functional class names of alcohols are derived by naming the alkyl group that bears the hydroxyl substituent, OH, and then adding alcohol as a separate word. The chain is always numbered beginning at the carbon to which the hydroxyl group is attached. Substitutive names of alcohols are developed by identifying the longest continuous chain that bears the hydroxyl group and replacing the E ending of the corresponding alkane by the suffix ol, or OL. The position of the hydroxyl group is indicated by number, choosing the sequence that assigns the lower locant, or numerical location, to the carbon that bears the hydroxyl group. Hydroxyl groups take precedence over or outrank alkyl groups and halogen substituents in determining the direction in which a carbon chain is numbered. The OH group is assumed to be attached to C1 of a cyclic alcohol and is not numbered. Nomenclature of alkyl halides. The IUPAC rules permit alkyl halides to be named in two different ways, called functional class nomenclature and substitutive nomenclature. In functional class nomenclature, the alkyl group and the halide, which could be fluoride, chloride, bromide, or iodide, are designated as separate words. The alkyl group is named on the basis of its longest continuous chain, beginning at the carbon to which the halogen is attached. Substitutive nomenclature of alkyl halides treats the halogen as a halo substitute on an alkane chain. The carbon chain is numbered in the direction that gives the substituted carbon the lower number. When the carbon chain bears both a halogen and an alkyl substituent, the two are considered of equal rank, and the chain is numbered so as to give the lower number to the substituent near the end of the chain. A very important reaction that takes place in organic chemistry is the reaction of alcohols with hydrogen halides, the SN1 mechanism. The SN1 mechanism, or substitution nucleophilic unimolecular mechanism, is characterized by a two-step process. The first step is the rate-determining step and is the ionization of an alkyl halide to carbocation and a halide ion. Here is an example of this type of reaction, and it is the formation of tert-butyl chloride from tert-butyl alcohol and hydrogen chloride. This right here is the overall reaction, and then here are the steps of the mechanism. Step 1 shows the protonation of tert-butyl alcohol to give an alkyl oxonium ion. Proton transfers from strong acids to water and alcohols rank among the most rapid chemical processes and occur almost as fast as the molecules collide with one another. That is why the transition state in this step is fast. Step 2 shows the dissociation of tert-butyl oxonium ion to give a carbocation. The transition state for formation of tert-butyl cation from the oxonium ion is the point of highest energy, which makes this the slowest step. It is called the rate-determining step and the overall reaction cannot proceed any faster than the rate of this step. Step 3 shows the capture of tert-butyl cation by chloride ion. The transition state for this step is fast because the activation energy required is small, and the bond formation between a positive ion and a negative ion occurs rapidly. Moving on to alkenes. Alkenes are hydrocarbons that contain a carbon-carbon double bond. The double bond is the site of most of the chemical reactions that alkenes undergo. Alkenes pretty much resemble alkanes in most of their physical properties. Alkenes with more highly substituted double bonds are more stable than isomers with less substituted double bonds. Alkenes are also known by the older name olefin because they form oily liquids on reaction with chlorine gas. Alkenes are prepared by elimination of alcohols and alkyl halides. Preparation of alkenes by elimination reactions of alcohols. Elimination reactions are a type of reaction in which a double or triple bond is formed by loss of atoms or groups from adjacent atoms. An example of this type of reaction is the dehydration of alcohols. Dehydration requires an acid catalyst. The order of reactivity of alcohols is tertiary, greatest, secondary, and then primary. Elimination is regioselective, which means the reaction can produce two or more constitutional isomers, but gives one of them in greater amounts than the other. The reaction proceeds in the direction that gives the most highly substituted double bond. When stereoisomeric alkanes are possible, the more stable one is formed in greater amounts. An E1 mechanism, or elimination molecular, via a carbocation intermediate is followed with secondary and tertiary alcohols. Primary alcohols react by an E2 mechanism, or elimination by molecular. Sometimes elimination is accompanied by rearrangement. This image right here shows the general equation for this type of reaction and then an actual example of this type of reaction. Preparation of alkenes by elimination reactions of alcoholides. An example of this type of reaction is the dehydrohalogenation of alcoholides. Strong bases cause a proton and a halide to be lost from adjacent carbons of an alcoholide to yield an alkene. Regioselectivity is in accord with the Zaitsev rule. A concerted E2 reaction pathway is followed. Carbocations are not involved and the rearrangements do not occur. An anticoplanar arrangement of the proton being removed and the halide being lost characterizes the transition state. This image shows the general equation for this type of reaction, and then an actual example of this type of reaction is shown here. That concludes my presentation. Thanks so much for tuning in.